16 questions first, the single choice ones first, and then we'll go on to the multiple choice questions, right? So this time, there was a healthy mix, I guess, of inorganic and organic. A lot of questions from organic as well as physical chemistry were there. Inorganic was relatively less, not too many questions to be honest. Some of the questions were from, I mean, many of the questions were mole concept related. Some questions related to our organic were related to stability of free radicals or carbocations and stuff like that. And let's look at the questions one by one. We'll discuss all the solutions to the questions one by one. Calculation, of course, you have access to calculator, I suppose. So some of the calculations were not that easy, to be honest. But yeah, not very tough, complex questions. Some of the questions from inorganic were based on heating effects of salts and stuff. Okay, let's look at these questions one by one. Yeah. So the first question here is mole concept based. Mixture of hydrogen and chlorine kept in a closed flask at a constant temperature was irradiated with scattered light. Hydrogen and chlorine would give us HCl, right? And after a certain time, chlorine content decreased by 20% compared with that of the starting mixture, and the resulting mixture had composition as follows: 60% by volume of chlorine, 10% by volume of hydrogen, and 30% by volume of hydrogen chloride. So determine the composition of the initial gaseous mixture. So we started off with hydrogen and chlorine. What percentage was there is the question, right? So I mean, of course, you can take any value per se. I mean, there is no specific mention about the volumes. You can even start with like 100 as the total, 100 ml as volume total, and from there we can proceed. Of course, the reaction here is between hydrogen and chlorine, which is H2 plus Cl2 giving us 2HCl. So of course there is no volume change as far as this reaction is concerned, because 2 moles is giving us 2 moles. Assuming ideal behavior here, we can say that there is no volume change on reaction, right? So let's say that at time t equal to 0, okay, at time t equal to 0, let's say that we started with x moles of x ml of hydrogen and 100 minus x ml of chlorine, right? And no HCl. And after time t equal to t, some time t equal to t, when the reaction is done, after a certain time is all that they have said. So not specifically any particular time. So after some time t, let's say V volume reacted, right? So V volume of hydrogen reacts, then V volume of chlorine will react, because this is a 1:1 mole ratio reaction, right? And 1 mole is giving me 2 moles of HCl. So if this becomes X minus V, this will become 100 minus X minus V, and this will become 2V, right? Now, what is given is that eventually it was 60% by volume of chlorine, right? So, as I said, we could have done like with a generic volume because nothing is specifically given to us. But I took 100 as the total volume, and volume is not changing when the reaction is taking place. So eventually, also it will be 100 ml, and within that 100 ml, 60% is chlorine, which means that this is basically 60, and 10% is volume of hydrogen, which means that this is 10 ml, right? Out of 100 ml, 10% is 10 ml, 60% is 60 ml, and the remaining 30% is that of hydrogen chloride, is what is given to us. So 2V is something that we know. So 2V is going to be equal to 30, which means that V will be equal to, from here we can see that V will be equal to 15, which means that 100 minus x minus 15 is 60, right? So which means that 100 minus x minus 15 is 60, which means that what is x? 100 minus x minus 15 is 60, which means that 85 minus x is 60, right? So 85 minus x is 60, which means that x is equal to 25. So we started off with 25, and 100 minus x is 75. So the correct answer here is obviously D option, 25% hydrogen 75% chlorine. So if I had like 100 ml total, 25 ml hydrogen, 75 ml was chlorine. From there, of course, V was 15 ml. So 15 ml of hydrogen reacted, 15 ml of chlorine reacted. So 60 ml chlorine is left, 10 ml of hydrogen is left, and 15 ml is going to give us 30 ml of HCl. So that is exactly what we want, right? So our correct answer here for first question is D, 25%, 75%. Next question. A research scholar requires 50 ml of an aqueous sodium nitrate solution containing 70 milligram Na plus per ml, right? So milligram, 70 milligram per ml. And what is our volume? Total volume is 50 ml, which means that weight of Na plus is going to be equal to 70 milligram per ml into 50 ml, which is going to be equal to 3500 milligram, right? Ml cancels, and we'll get 3500 milligrams, which is what, 3.5 grams. Now, obviously, NaNO3 has one sodium per formula unit of NaNO3. So obviously, number of Na plus and number of NaNO3 are going to be the same, right? So let's find number of moles of Na plus first. Now, Na plus has the same weight as Na, right? 23, right? So Na plus, because you're removing an electron. So cation has the same, almost same weight as that of your atom, because obviously electrons are very negligible in weight compared to the rest of the nucleons that we have, right? So number of moles of Na plus will be 3.5 divided by 23, right? And sodium 23, assume, right? The If 22.7 was given in the data, I don't have the data page per se. So if 22.7 or something else is given as the mass, then accordingly we'll have to change the calculation a bit. I'm taking 23 out here, right? And the amount of NaNO3 is required. Now this, as I was telling you, each NaNO3 contains one Na. So this is also equal to the number of moles of NaNO3. So weight of NaNO3 will be number of moles into molar weight. So that will be equal to 3.5 divided by 23 into 23 plus 14 plus 48. 62 plus 23 is 85, right? So obviously, I mean, I'm looking at the answers here. They are drastically different from each other, right? So I am going to do approximation. Obviously, I don't want to do the exact calculation. So 23 into 4 would have been 92, and 23 92, which means that 85 is like 7 short of that, right? So this is 7 by 23 is what, 1 by 3 ish, roughly, right? So this is somewhere around 3.7 maybe, right? I'm not doing the exact calculation, but yeah, a rough look at this, because I mean, I can see all the answers are drastically different, right? So this 3.5 into 3.7, obviously I can see both of these numbers are less than 4, so it should be less than 16. And I can see a 12.93 here, which is the only answer in this range. So yeah, I'm going to assume that this is probably 12.93. I mean, obviously not 3.5 into 3.7. If you do the exact calculation, I'm guessing you're going to get 12.93, around 13, right? So 3.16 is the root of 10, right? So this is both greater than that. So yeah, obviously it should be greater than 10, 11 and stuff. So I'm getting 12.3, 12.93, D option as the correct answer. Moving forward, third question. A sample of crystalline soda A with mass 1.287. So these are the things where, calculation gets a bit tricky. But then, because the numbers options here are decently far away, I mean, 5, 6, 7, 10. Let's read the full question first. In fact, sorry, right? So a sample of crystalline soda. Of course, we are speaking about Na2CO3 here, right? And with this is crystalline form. So what does that mean? We'll come to that soon. With this much mass was allowed to react with an excess of hydrochloric acid, and excess of hydrochloric acid means that whatever is the amount of Na2CO3 we have, that is the limiting quantity that is there. That is the limiting reagent that is going to be there. So that is going to decide how much of reaction is going to take place. HCl we have in surplus. And 100.8 ml of a gas was liberated, measured at STP. Okay. Fine. How many molecules of water in relation to one molecule of Na2CO3 are contained in the sample of soda? So yeah, first of all, it can't be called a molecule of Na2CO3. It's a formula unit of Na2CO3. It's a ionic compound that we have. It's a crystalline ionic compound. So this is probably based on the question. This is probably some Na2CO3 dot XH2O, right? So this is the molecular formula. I mean, molecular formula of this compound. This is the formula of this substance, right? And I'm supposed to find out this X out here, right? So the point here is, what is our reaction going to be? Na2CO3 plus HCl. I mean, of course, dot H2O is also there, but that is not going to participate in the reaction, right? So plus HCl giving a balancing, I'm going to get 2 NaCl. So what we have is sodium carbonate, right, which is a salt of strong base sodium hydroxide and weak acid, carbonic acid, H2CO3. When a strong acid like HCl is added to salt of a weak acid, strong acid is going to displace that weak acid and it's going to form its own salt. So HCl has formed its own salt NaCl, and along with that, I'm going to get H2CO3 per se. But yeah, of course, in the course of the reaction, there is enough energy that is there. This is also a neutralization reaction. Your H2CO3 is going to break down into H2O plus CO2, right? So they are speaking about this is obviously in solution, hydrochloric acid solution that we have. Hydrochloric acid is otherwise a gas, right? So the solution that we have, H2O is going to remain there, and what is going to come out as volume of gas is this CO2, right? So we have probably studied about this. Carbonate salts has that brisk effervescence of a colorless, odorless gas that turns lime water milky. They could have given this as an extra hint, but yeah, I mean, I'm sure it's pretty clear. This is the reaction that is happening. So we have volume of carbon dioxide given to us, right? From there, we can find number of moles of carbon dioxide, which is 100.8 ml divided by molar volume, right? STP. So strictly speaking, if just STP is given, I'm going to take 22,700, right? So 22,700 ml per mole is the molar volume, right? So this is supposed to be equal to the number of moles of Na2CO3. Now think about this. Each mole of this is going to give me 1 mole of CO2, right? Each Na2CO3 is going to give me 1 mole of CO2. So each Na2CO3 dot H2O is also going to give me 1 mole of CO2. So number of moles of these two things should be the same, right? So here this will be equal to number of moles of our Na2CO3 will be 1.287, the weight of the sample, divided by molar weight of this, right? So molar weight of our crystalline salt with water of crystallization will be how much? Na2CO3 is 106, 46 plus 12 plus 48, 106 plus XH2O. H2O is 18 into X will give me the weight of water of crystallization. That plus 106 is going to give me the molar mass of this salt. So 1.287 divided by this is supposed to be equal to this. Now I'm supposed to cross multiply and get the value of basically our X. That is the story. And I'm again, like as I mentioned before, I don't want to use a calculator. You can easily do it with a calculator, but yeah, I'm just trying to do approximation as much as possible, right? So this is 100.8, which is as well as 100. 101, if you want to take approximation, that is fine as well. So yeah, 106 double zero would have been with 100, right? And 101 would have given me 10600 plus 106, which would mean that this plus 106. Of course, if you want to do the exact calculation, then do zero point 0.8 into 106. 0 0.8 into 106 is what? 10.6 into 8, 80 plus 4.8, 84.8. If you want to do that, yeah, do it, but 84.8, right, is equal to 1.287 into 22,700, right? So this is 22.7 into, of course, sorry. Along with this, we have 1000, 18 into 100, 1800 plus 18 into zero point 0.8 is what? 8 into 1.8, 8 plus 6.4, 14.4. So 1814.4 X. Oh, wait. 1814 also is going to give us the correct answer, I'm guessing. Right. So this is 22.7 into, I'm taking three decimals to the side, so it will become 1287. This is what we have to solve, right? And from here, I'm going to get the value of x. What will be the value of x? As you can see here, x will turn out to be equal to this, which is 22.7 into 1287 minus 10,684.8 divided by 1,814. This is going to give me the final answer, right? So, of course, is that some kind of an easy calculation that I can do? Maybe I'm very comfortable with doing approximation. What I feel like doing is to take away three decimals straight off, convert the denominator into 1.8, and like three decimals would mean 10.6, and three decimals would mean 22.7 into 1.287, which I'm going to take it as 1.3. This will give me a calculation which is going to happen much faster. If it is 5 or 6, 4, 5, 6 are three numbers which are dead close to each other. So if it turns out to be one of these, then it would be more sensible to do a calculation, proper calculation. But one answer is 10, which is far away from all of these. So when I'm looking at this calculation, I mean, I can see this is 22.7 into 1.3. 22.7 into zero point 0.3 would be around what, 69-ish, right? 6.9. So 22.7, 23 plus 6.9, this is roughly around 30, right? So 30 minus 10 divided by 1.8. So around 20 divided by 1.8 or something like this is what I'm seeing. So this is very close to 10. I mean, if I'm going to do the exact calculation, I'm going to probably get it as 10. Of course, I have to keep in mind at the same time that when I took three decimals to the left and changed it to 1.287, instead of that I took 1.3, right? So that my answer is obviously going to be greater than the actual answer. So even this, I'm getting it as 30, 29 something minus 10 point something, 11-ish, and divided by 1.8. So 29 minus 11 is around what, 18, divided by 1.8, somewhere around 10. And I mean, obviously, if I did the exact calculation, I'm going to get 10. And it's almost never expected that you would do exact calculations if your numbers are like these, right? So if it was to be something like, oh, 3.453 and something like this, and 3.12 and all of these, there it would have made more sense to do an exact calculation. But yeah, even just approximation can give me this answer. I'm clearly seeing that this is 10. So our correct answer here is D option, 10. Right? Let's go to the next question. This is based on heating effects of ammonium salts. Ammonium salts are generally like, because NH4 plus is a large cation, generally they have very low lattice energies. These are, kind of the most of these ammonium salts do tend to kind of sublime, generally breaking down first into ammonia plus the acid that made this salt in the first place. So here the question says, which of the following ammonium salts releases sulfur trioxide gas on thermal decomposition? So this is little bit of an information. Sulfates, within sulfate, ammonium sulfate does have this thing that when you are heating it, first you are going to get ammonium hydrogen sulfate or ammonium bisulfate, which in turn further, right? So ammonium sulfate, NH4 twice SO4, first on heating gives you somewhere around 250 to 40 degrees. It begins to melt, and first you end up getting ammonium bisulfate, which further on heating eventually breaks down into ammonia, and then like your sulfur trioxide is not obtained here. Sulfur trioxide, your sulfuric acid, that part of SO4 2 minus, it gets reduced to sulfur dioxide, and your ammonia is kind of oxidized. Nitrogen is oxidized into N2. So what you end up getting here is ammonia, sulfur dioxide, and nitrogen, not sulfur trioxide, right? So, but yeah, the next one that is there, ammonium, this is This is peroxide sulfate. Yeah. So H2O8, ammonium peroxysulfate is peroxide sulfate rather is going to give us oxygen. So this is the information, of course, inorganic. This is the heating effects of salts that we are looking at. What we end up getting in the second one, right, is going to be your sulfur trioxide. So here we have H2O8 in which there are peroxide sulfate is like this. So here you have two oxygens which are in -1 oxidation state, and these are the ones that get oxidized, right? And what you end up getting here is sulfur trioxide, along with, of course, oxygen and ammonia, right? So, of course, I'm not writing the exact balance reaction. So here, the SO3 is what is formed, not sulfur dioxide, right? So this is heating effects of salts. Ammonium salt, specifically ammonium sulfate. Ammonium chloride, I'm sure you know, ammonium chloride breaks down into ammonia and HCl. And as far as ammonium peroxide sulfate is concerned, you're going to get SO3. So the question said which one releases SO3, and obviously the correct answer is two only, which is B. Right? Ammonium sulfate does not. The next question is this is a nice question. Uh, Kind of inorganic, yeah. Of course, information that you know from many different places are used up here, to be honest. Which of the following groups contain your solid compounds at 10 degrees Celsius, right? So H2O is a liquid. Of course, at 10 degrees, we know H2O is a liquid, so that straight away goes out of the window. The next one, of course, methane is a gas and ammonia is a gas at 10 degrees Celsius. So these are none of these are solids in A option. B option, you have fluorine and chlorine, which are gases. Bromine is a liquid, right? So B option also goes out the window. There is no solid at all in these two. In D and C is where probably our answer is going to be, right? So as far as D is concerned, silicon, of course, is solid under room conditions. Crown sulfur is also solid. But you have the third thing given here is CS3, COCS3, which is acetone, which is liquid at 10 degrees, I'm guessing. I don't think its melting point is about 10. But yeah, this is a liquid under 10 at 10 degrees at least. Now, as far as C option is concerned, of course, this is going to be our answer. Iodine is a solid under the room conditions and all, and under 10 degrees Celsius. NaCl is, of course, an ionic solid. And as far as sulfur trioxide is concerned, even sulfur trioxide exists as a trimer, SO3O9. You might have come across this. SO3O9 ends up having this shape like this, primer of sulfur trioxide, which ends up being a solid, right? So this is a solid. Sulfur trioxide is a solid at 10 degrees Celsius. It has a melting point of around 15, 16 degrees Celsius, I guess. And so, of course, this was kind of obvious. I mean, the A option, B option is straight away out of the window. And the in D option, acetone is something that you know is a liquid, right? Around room temperature. And of course, this is the correct answer here. C option, sulfur trioxide, iodine, and sodium chloride. Right. Now, next is the organic isomerism based question. So here they are asking us how many possible 1 degree, which means like primary amines are possible for this formula C5H13N, right? So, I mean, 1 degree amine would mean that you have an NH2 group, and then remaining, what do you have? You have C5H11. So, C5H11, you can understand is your pentyl group if you want to think of it like that, right? So because it's like one hydrogen short of your pentane, right? So C5H12 is CnH2n plus 2, which is your pentane. So C5H11 is the group that you can obtain by just removing one hydrogen from there, right? So there are different possible 1 degree amines that we can get. The simplest one, when you have like your normal pentane, pi carbons in a chain, and you have your NH2 group here. This is one. This is your one amino pentane, right? So this can be here. Of course, I can change the position of these one by one and get different possible isomers. So within this, with n-pentane, I can also have NH2 here, right? One more option is there when I put it here, right? So let me draw all of them one by one, right? So, and the third one would be something like this, C, 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 straight chain. NH2, right? So this is one pentanamine, two pentanamine, and three pentanamine, right? So these are the three possible, pentane, normal pentane types, isomers that are possible out of these. Now I can have butane based. So let's say I have this, right? So this is your 2-methyl 2-butanamine. So I can have my NH2 here, right? Then, oh, in fact, I should have kept one color for all pentanes and stuff like that. That would have been more easier to kind of spot. But yeah, okay. So with butane, now this is where one amine can be there. The same amine can be sent to the terminal carbon as well. So C, 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 and NH2 here. So this is 2-methyl butane, one amine. So butane, two amine. Now, if I change my position of amine to this third carbon, if I put it here, then I can get one more. So I can have this one. This is another possibility, right? This is another possibility. Now, how many are done already? Six already done. Now I can also send, maybe I can send it to a butane types group. Yeah, of course. Right. So I can probably try something like this. Is there any more possibility as far as NH2 can come here? Of course, anywhere I send NH22 in the neopentane thing, they will all be the same, right? They will all be exactly the same. They will all be 2 methyl, right? 2 dimethyl rather propanamine, and this is still butane. I'm guessing how many have we reached so far? I've seen one here, second here, third here, fourth here, fifth here, sixth here, seventh here. Is there anything else that I can think of? Maybe with a butte. Hmm. Of course, if you're going to put, uh, let's say something like this, one, two, three, four, and I send C here, then it turns out to be same as these, right? So, I mean, like we look at the carbon atoms in a straight chain. So this is not different. You can't just put a methyl here per se. So what else? With pentane, I had three. With butane, I had one, two. I can also, so if you are going to send, let's say, for example, C here and an NH2 here, that is not any different from this one, right? So when you are looking at, which one was am I talking about? Which one am I talking about? So this one, if you look at this, that is the same as this, right? So you have NH2 on the terminal carbon, and on the second carbon you have a methyl group attached. So this is not different from 5, right? So this is the same as 5. So that is not possible. Now what I could have is a ethyl group on our, oh, okay, let me try that. I'm not very sure it's any different. Let's try nonetheless. Let's see. Maybe if I take C, C, C. Okay. And on the middle one, if I put a C and next to here and then here. Is this any different from which one is this? This looks very much similar to at the second position I have methyl and the third one I have okay. So I mean it's the same, right? So this is the same as six that we have drawn. What else is there? So we have six, seven, eight, and nine. We have already seen seven, right? Primary amine is what I need as well. So on the terminal one, on the second one, on the third one, butyl, just confirming that there is nothing else out here. Right, so I have an amine with butane on the terminal one. Oh, I can send NH2 to the terminal carbon as well on the other end, right? So I think if I do this, CCCC, and put a CH3 here and an NH2 here, this is different, right? This is, of course, yes, this is different from all others that I've seen. Butane, where did we have 5, 6, 7 were bute, right? No, 4, 5, 6 were mute. And in this, we had amine on the second one. In this, we had amine on the first one and methyl on the second one. In this, we had amine on the second one and methyl on the third one. And here we have amine on the first one and methyl on the third one, right? Yeah, so this is also one more. I can't imagine any other that I'm seeing here. No, I'm guessing this should be it, right. So we have in all eight isomers, which are primary amines, which have the formula C5H13N, right? Now, the next question is from organic. From the compound given below, the correct increasing order of CH bond strength is, right? Now, when you are looking at bond strength, bond energy is parallelly what we are looking at. Bond energy generally refers to giving energy to break this bond down, and generally, bond energy is also related to homolytic fission, right? So you are breaking it down, you are not converting it into, like, I mean, if you're thinking about, let's say, something like an acidic character in hydrogen, that's a different story. If you want to make H plus, that would have been different. But what we are doing is we are breaking it down homolytically. And when we break it down homolytically, we are going to get like a free radical. And when you are looking at a free radical, we have to look at the stability of the free radical. So if the product obtained is very stable, this is going to be easy to make, which means that the bond energy is going to be strong. Other way around, if the product is unstable, then obviously doing this is difficult, which means that the bond energy is going to be more. That is the logic that I'm going to use here, right? So what do we have? We have HA, HB, and HC. Let's try to identify what these are going to end up doing, right? So as far as your HA is concerned, you can see it's the one that is attached to a methyl carbon, right? So a normal carbon, a tetrahedral carbon, sp3 hybridized carbon. Now, as far as hydrogen B is concerned, even that is in on an sp3 carbon. But when I get a free radical here, like let's say if I'm breaking it down and you end up getting a dot here, or a dot here, or a dot here, I have to look at what exactly is the stability of these. Whenever the stability of the product is low, what I'm going to, so first, after removing this is what I'm saying, right? So after removing these, the dot, dot, dot that we had is the free radical that we are talking about, right? So as far as this B dot is concerned, which is like wedged between the two phenyl groups, right? So you, when you have your benzene ring, that is something that has resonance, and that is always going to be something that can lead to stabilization, right? So free radical stabilization is going to happen something like this. You have your benzene group. Let's me draw it with the double bonds like this, and then you have, let's say, I'm not drawing the whole thing once again. I'm just going to say that there is a carbon here with a dot here, right? So what happens as far as resonance, drawing resonance structures is concerned, you can think of this double bond breaking with half hook arrows like this, right? So what that does is you are going to get this dot, and this carbon is also having a single electron, and there is a dot here, and the other two I'm going to leave it as it is, right? Now this dot and dot, at the top here are going to convert into a double bond. So the double bond has essentially shifted here, right? And then the free radical single electron that you have, odd electron that you have, that has come into the ring. Now this is going to shift here. I mean, in the same format. I'm not supposed to, strictly speaking, put the whole arrow here because yeah, I mean that means something else. That's a whole shift of the two electrons. Instead, the same half hook arrows that we had here is going to give us the next, which is going to be this, right? The next resonance structure that we are going to get is going to be this. And then the same thing happens here, and what we are going to see as the next possible free radical resonance structure is this. The double bond is basically going to shift down. This is there, and then you have this double bond here, right? I mean, of course, you don't have to draw a carbon there in our bond line structure. So this is what we are going to get. And after that, once again, now this is going to again have that half hook story here happening, and then the dot and dot, your odd electrons are going to bond, and then you are going to get this once again the original, but of course with the locations of the pi bonds having shifted. Of course, these are individual resonance structures. What we just mean to say is that each benzene ring is going to cause some level of stabilization, right? So as far as this free radical born out of hydrogen B, removal of hydrogen B is concerned, that is doubly stabilized, right? So there is one benzene ring on the left and one benzene ring on the right side, which tells us that it's going to be doubly stabilized by this particular free radical formation. So, of course, that will be the most stable free radical that I'm going to see, which means that this hydrogen B removal is going to be the easiest, which means that it is going to be the weakest, right? Which is there in both B and D options. And when I'm looking at hydrogen C, that is in the methyl group, which is fine, which is okay. I mean, some amount of stabilization is there. This ring is attached to this carbon, so of course there is going to be stabilization, but it only has that one ring which is going to stabilize it, not two rings like what was there in B, right? So this is also decently stable. And as far as the hydrogen C is concerned, that is going to cause a free radical to be there within your, I mean, it can be said to be what, a vinyl position of such, which is inside your benzene ring. And this is a sp2 carbon of sorts and more electronegative one with a dot on it, which is not very stable. So removal of C is going to cause us a bit of an issue, right? So it's not a very stable product that is formed here, which means that the removal of C is going to be the most difficult one, which means that hydrogen C carbon is going to be the strongest. Then you have your hydrogen A carbon, and then you have your hydrogen B carbon, which will be the easiest to remove because that will give you the most stable free radical intermediate, right? So, what is our correct answer? It's going to be D option, right? Cool. The next question is based on again chemical bonding. You can think of it as based on hybridization, based on bonding. So, here we have CO bonds X, Y, and Z, and we have to look at the increasing order of carbon oxygen bond length, right? So, yeah, of course, resonance stabilization and all are going to come into picture, but looking at this picture, we do see that carbon oxygen, the X bond that is there, is a double bond. It is going to be the shortest, right? So a double bond is shorter than a single bond. The other two are single bonds, right? Carbon oxygen single bond, carbon oxygen single bond. But if I'm looking at this carbonyl carbon, the one where that X and Y, both of these are there, this carbon is sp2 hybridized, while this carbon is sp3 hybridized, right? So obviously we know that sp2 has more percentage S character and is going to be shorter bonds. uh, Bond order is like something that you can use to speak about bond length, obviously. So X here is a carbon double bond oxygen, right? So obviously this is going to be shorter, and carbon that is there, that carbonyl carbon is sp2 hybridized. So obviously even this this and this, all three of these are going to be relatively shorter because sp2 hybridization automatically tells you that it's a shorter orbital, shorter bond that is going to be there. So yeah, then carbon oxygen, this Y and Z, both of these basically are single bonds, carbon oxygen single bonds. So how do I distinguish between them? So bond order is not going to help. Hybridization is going to help. So yeah, of course, this is sp2 carbon on the left, carbonyl carbon, and on the right you have your methyl group attached to oxygen, that is an sp3 carbon. So it is going to be longer. So the shortest here is obviously going to be X, then you have Y, and then you have Z, right? So X, Y, Z is the order that I can see in B option. So that is our correct answer. First, another way of thinking about this is how there is also going to be a resonance, which is something that is going to give us a product in terms of resonance structure, if you want to call it like this, although not very stable, but something like this. So there are two lone pairs on this oxygen, and that one of them is in conjugation with the double bond. So that lone pair comes into this zone, and it's going to become a double bond between that oxygen and carbon, carbonyl carbon, and this pi bond is going to shift on oxygen. So you end up something like this. Of course, if I look at this, then it feels like this is a double bond, this is a single bond. This should be longer, but yeah, of course, the carbonyl carbon oxygen is a double bond as given in the structure. So of course X is going to be the smallest, then you have your Y, and then you have your Z, right? So which is B option. Let's go to the next question. Again, same story. Carbon hydrogen bond strength is that is discussed, right? The correct order of bond energy of different CH bonds in the given compound. So again, what we have to think about is, what if I break this homolytically? What is the kind of free radical that I'm getting? If it is stable, then I can say that bond energy is going to be less, right? Now look at this. So this is a primary carbon that you have, right? So the structure is drawn like this. Of course, it's never at 90 degrees. So it is going to be a benzene group with a ethyl group, somewhat like this in this sp3 kind of angle. There are two hydrogens there. So our hydrogen one is either of these, and as far as the terminal hydrogens, the three of them are there. One of them is basically your hydrogen 2, and one of these is basically your hydrogen 1, and one hydrogen is the one that is there in the benzene ring, right? So you end up getting a free radical on an sp2 carbon, which is not very good for us. So hydrogen 3 is going to be relatively difficult to break apart. So that should have higher bond energy. Now, as far as these two free radicals out of hydrogen 1 and hydrogen 2 are concerned, of course, when we remove hydrogen 1, it becomes this carbon that is attached to, wait, what is it too long? So this is the other H1, right? So H1 is a type, right? That we are speaking about here. And then you have your CH3, and then you have your benzene ring. So here the free radical is in conjugation with the benzene ring. So there is resonance stabilization that can happen. So this is going to be the one that is going to be the weakest hydrogen, carbon hydrogen bond, because once you remove this, once you break it homolytically, right? Once you give bond energy is supposed to break down bonds and just like send the electrons back to the original atoms. So if I'm getting a free radical here, that is going to be the most stabilized one, which means that the carbon hydrogen one is going to be the weakest bond that is there. And then you have your methyl group, which is a sp3 carbon, and you have a free radical there. That is going to be your hydrogen 2 that was there. Huh? So of course, the most difficult would be to remove the one that is within your benzene ring. Speaker got disconnected for some reason. Sorry. So if I have a free radical at this position, this hydrogen C, then like we saw in that earlier question, this is in conjugation with this double bond. So there will be this half hook arrows or like a homolytic breakage of your double bond, pi electrons. And you can then see that the double bond will shift here. And what you're going to get is this, right? What you're going to get is something like, wait, what you're going to get is this. So there is some amount of resonance stabilization that is there in hydrogen C, which is the best, right? So this is a second degree hydrogen, of course, that is there, second degree carbon or a secondary carbon. And hydrogen D is also the same. It is attached to a secondary carbon, but of course, there is no conjugation with the double bond that this one has, right? And as far as hydrogen E is concerned, that is a tertiary one, right? So that hydrogen E is attached to a carbon, which is attached to three other carbons. So plus on top of that, if I'm removing it and if I get a free radical here, you can understand that is in conjugation with the double bond. That double bond can shift here. So there is some amount of resonance stabilization that can happen. So E, I mean, between free radicals, like something that is stabilized by a benzene group or something like this is very stable, and very stable means that the bond strength is low, right? So the correct order of abstraction, who can get abstracted the most? E, because that free radical would be resonance stabilized as well as being on a tertiary carbon. So yeah, E is going to be the one that is most easy to abstract. Then of course C is going to be the one because it is also resonance stabilized. And between like A and of course B is going to be the worst because it's on an sp2 carbon that you are ending up with a free radical, and it is that vinylic kind of a position which is very bad, right? So it's on a carbon with a double bond, so it's not in conjugation with anybody, it's on a so this is going to be the worst one to remove, right? So worst to remove, and the least chances will be that of this to get removed. So I'm looking at EC and blah 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 B, right? So between A and D, of course, A is a primary one, so that is the least, and D is a secondary one, not resonance stabilized, but yeah, at least secondary one, so relatively stable compared to your removal of hydrogen A, which is going to give me a 1 degree primary free radical, right? So the correct order of abstraction is ECDAB, which I can see is the C option out here, right? So this is my answer here. Next question: which of the following will form foam, right? So, in water containing Ca2 plus and Mg2 plus. So this is like based on hard water, hardness of water, right? So something that we study in hydrogen chapter, G, right? So Ca2 plus and Mg2 plus ions are there, which means that this is your hard water, and which of these will form is the question, right? So when you're looking at soaps, we know that soaps are going to like create scum, right? With your, I mean, basically the calcium and magnesium salts of these soap fatty acids would be the scum which kind of prevents it from being a surfactant. It prevents it from behaving like something that can form up, right? And bubbles and all will not be created. So as far as sodium palmitate or barium stearate are concerned, stearic acid, palmitic acid, both of these are the ones that are typical soap kind of substances that we have. So both of these are not going to do it, right? So both of these are going to just create scum. But yeah, of course, this is a detergent, a synthetic detergent, potassium N-dodecyl, normal dodecyl benzene sulfonate, right? So this is something which is a synthetic detergent, and it is going to still cause foam, right? It will not form a precipitate, it will not form a scum with your calcium and magnesium salts. So what you're going to see is that the C option is going to form. Of course, all of these is not right because, yeah, soaps won't be forming immediately. I mean, of course, once all the Ca2 plus and Mg2 plus goes away as scum, gets removed as scum, then of course even they will form. So that is kind of technically a incomplete question. I mean, like if you're using excess of all of these, eventually form will be there, right? But initially a little bit of scum will be produced. So immediately forming will not happen in A and B, but C will definitely give you form irrespective of we have just added a little bit or not. So yeah, so correct answer here is of course C option, right? Now we'll go on to the multiple correct answer type questions. So the pair of elements which must have equal number of electrons in the outermost shell. Uh, Periodic properties, electronic configuration, atomic structure, whatever you want to call it, right? So sodium and strontium, right? Strontium? No, strontium is the second period, right? So sodium is first period, alkali metals and beryllium, magnesium, calcium, strontium, and barium are second period. So obviously, sodium has one electron in the valence shell, outermost shell. Strontium has two electrons, so not right. Selenium, tellurium, of course, works. This is your oxygen family, so they all have that S2P4 kind configuration. They will have six electrons, right? So oxygen, sulfur, selenium, tellurium, polonium, right? So selenium and tellurium are obviously going to have same number of valence electrons. So this is obviously a correct answer. Equal number of electrons in the outermost shell. Oh, okay. So in that case, even MnFe is going to work. Manganese is atomic number 25. So manganese, what you get is your 4s2 3d5. Of course, 3d5 is an inner electron. So as far as the outermost shell is concerned, that is your fourth shell that has two electrons. Iron is atomic number 26, and what you get is 3d6 4s2. But yeah, you can see outermost shell, the fourth shell is having two electrons even here. So even this is a correct answer. We had a multiple correct answer question, right? Arsenic and bismuth. Of course, even this is also going to be correct. Nitrogen, phosphorus, arsenic, antimony, and bismuth. All of these are the ones with S2P3 kind of configuration. So arsenic and bismuth are also going to have S2P3 5 electrons. So even this is going to be a correct answer. So what are the correct answers? B, C, as well as D options, right? So let's go to the next question. The correct statement is R. The pH of 10 to the power minus 8 molar NaOH. This is a weird question that is there. I mean, this is something that we typically say in ionic equilibrium when we speak about pH of ultra dilute strong acids or strong bases, right? Ultra dilute. So when you're looking at 10 to the power minus 8 molar, this is really low, right? So there might be an inclination to say, oh, OH minus is going to be 10 to the power minus 8 molar, which means that pH is equal to 8. No, wrong. Why? Because OH minus is not going to just come from NaOH. Of course, from NaOH, we are going to get 10 to the power minus 8. But then we have the equilibrium of water, right? Water itself, when nothing else is added, is already giving us 10 to the power minus 7 molar each of H plus and OH minus at 25 degrees Celsius. So they should have also mentioned the 25 degrees Celsius angle to it. But yeah, this is going to be there, right? So whenever you add a strong acid or a strong base, what generally happens is that because of Le Chatelier's, you can think of this equilibrium shifting backwards. And when it shifts backward, water gives so less H plus and OH minus that we generally consider H plus OH minus from strong acids or strong bases, right? But here we have strong base NaOH, but it is very, very dilute. So it is only 10 to the power minus 8. Oh, wait, I should have said POH here anyways. But yeah, I mean, it was a wrong thing anyways. Not very worried. So yeah, is pH going to be equal to 8? In this case, no, because pH is going to be very close to 7. It's a very dilute solution of NaOH that you have. So it is not going to be 8, it is going to be very close to 7. Of course, slightly more than 7, maybe something like 7.0 to 7.3, maybe 7.2, even 7.2, 7 point, something like this, but definitely not 8. That is a very misleading kind of deduction. I mean, I can't say that 10 to the power minus 8 molar OH minus from NaOH is there. So POH is going to be 8, pH is going to be 6. No, right? So pH is going to be very close to 7 because this is a very dilute solution of NaOH, which is as good as water. Of course, NaOH is basic, so this has to be more than 7. But yeah, not definitely not 8, right? So A option is wrong. pH of 10 to the power minus 8 molar HCl is less than 7. This is true, right? So I mean, again, 25 degrees C angle is always there. This is the same story, ultra dilute HCl. So this is as good as water. So it's going to be very close to 7, right? So it's going to be 7, very close to 7, but it is going to be less than 7 because, of course, it's acid, right? So H plus this time around, right? So H plus coming from your HCl alone is going to be equal to approximately H plus from HCl is going to be equal to 10 to the power minus 8 molar, right? Not approximate, exactly, because HCl is a strong acid and it's ultra dilute HCl that we have, so it will have 100% dissociation. You're going to get 10 to the power minus 8 molar of H plus from HCl alone, but that is not going to decide your pH, right? Some amount of H plus is coming from HCl, which is less than even what was there coming from water, because water is going to give you 10 to the power minus 7 molar of each at 25 degrees Celsius. So this equilibrium is going to get pushed a little bit backward, but still we will see that overall H plus turns out to be more than 10 to the power minus 7. And what you are going to see is that the pH is slightly less than 7, right? If you want to do exact calculation, you can, but not required at this point in this question. Aqueous solution of FeCl3 is acidic. This is true. FeOH thrice, a weak base, a very weak base, and HCl is going to give you FeCl3, no? So this is a salt of a weak base and a strong acid. And whenever you have these salts of acids and bases, just think about what is the stronger component that is going to decide the overall nature of the salt. Of course, this is related to what you call the salt hydrolysis. This Fe3 plus is going to react with water. Fe3 plus is going to react with water. I mean, it is going to pick up OH from water and convert into FeOH2 plus and leave behind an H plus. If you want to write it as 2H2O and in the product you want to write 2H3 plus, it means the same. But yeah, this is what we have. So this process is called hydrolysis. Now further, it is going to pick up one more OH from H2O and convert into FeOH twice plus, right? So this is going to further convert into with water. It is going to give you FeOH twice plus, and then this is going to be with water and give you FeOH thrice. These second and third steps are not that relevant. It would happen a lot, which is a general observation that we speak of in ionic equilibrium. But yeah, point is salt hydrolysis is what eventually gives you acidic or basic nature to your solution. So you can see here that H plus is produced, which means that eventually this solution is going to be acidic, right? So this aqueous solution of FeCl3 is acidic. This is true, right? And then you have your Na2HPO2. Oh no, NaH2BO2 will react with NaOH to form Na2HPO2. This is wrong, right? So your H3PO2 is where you get this first salt from, right? So we had H3PO2, which looks like this. In H3PO2, which is our hypophosphorus acid, there is only one acidic hydrogen. This hydrogen is the only one that reacts with bases. So once that is removed, I'm going to get H2PO2 minus. And where is this H plus? Who is removing this H plus? NaOH, right? So NaOH plus H3PO2 giving you NaH2PO2 plus H2O. This is the only reaction that will take place. The other two hydrogens are directly attached to phosphorus. Hardly much electronegativity difference between these two. So these are not polar bonds. These are, I mean, polarity, slight amount of polarity is there, but not that polar a bond. This is not going to break. So what we say is that these two are not acidic hydrogens. They are not going to get attacked by an OH minus. A base is not going to be able to abstract this hydrogen. So of course, this looks, I mean, probably it looked like a correct answer, but it's not, right? So what do we have as correct answers? We have D as well as C options. Next one is information, right? So considering the hydrogen spectrum, direct information about hydrogen spectrum Bohr model. So the hydrogen spectrum series, correct the select the correctly matched pairs, right? So Balmer series N1 to N2, right? So, although strictly this is kind of weird, I mean, when you have any kind of N2 to 2 transition, this is what you call as your Balmer series. So that is exactly what is given here. I mean, strictly speaking, N1 and N2 are initial and final states, final levels, or shells or orbits, whatever you want to call it. So, strictly speaking, N2 is going to be 2 in your Balmer series. But what is this Balmer series? I'm sure you have heard about this hydrogen spectrum. So, you have your any transition to 1, right? Any higher level to 1 transition is called your Lyman series, and any transition to your level 2 is what you call as your Balmer series. Any transition to 3 is Bastian series. Any transfer to 4 is a bracket series. Any jump or transition to 5 is your Fund series. And then any transition to 6 is your Humphrey series. Right? So Balmer is N to 2, which is fine. Fund series, what we see here is 1 by lambda is r into wave number is r into 1 by 3 square minus 1 by n square. This is wrong. This is your Paschen series, right? So this is a transition from n to 3. Whenever you have a transition from some n to 3, we say that the formula for wave number, right? So Rydberg equation says that 1 by r, 1 by lambda, sorry, wave number nu bar, which is 1 by lambda, is r z square into 1 by n1 square minus 1 by n2 square. So if you are thinking about your Fund series, then it has to be any transition to 5, right? So not to 3. So if you are having a transition to 3, right? So you have some n to 3 transition, then of course our what do you call it, format of wave number would have been r into 1 by 3 square minus 1 by n square, but here they have said it is Fund series, so obviously this is a wrong statement. Then you have your Humphrey, which is n to 6, which we know is true. And Paschen series is in infrared region, true. Lyman series is in UV region. As far as Balmer series is concerned, you have 4 lines, the alpha, beta, gamma, delta, in what you call as your visible region in Balmer, right? This is ultraviolet is in your Lyman series. Balmer has 4 visible lines, and then all the others are higher energy lines, which are like kind of ultraviolet. And from then onwards, Bastian series, bracket series, Fund series, Humphrey series, all of these are energies less than visible region. They are all in infrared region. So what you're going to see is that this is also true. Right? So what are the correct answers here? A, C, as well as D. Now let's look at the last question that we have. Which of the following acids are stronger than benzoic acid? Right? So these are all substituted benzoic acid. You can see this is para hydroxybenzoic acid. This is para methoxybenzoic acid. This is para chlorobenzoic acid, and this is orthohydroxybenzoic acid. Right? So as far as this group is concerned, our groups that we have, right? So this is an OH group. It has a minus I effect, but it also has a plus R effect, right? So it has that plus resonance effect because it has lone pairs on them, right? So your oxygen atom has 2 lone pairs here. So of course that can go into the group, and that makes it what you call as a electron donating group, right? And same is the story with your methoxy group, right? OCH3. Oxygen has 2 lone pairs, so of course that can go into the system. When we speak about acid strength, the idea is we look at the conjugate base, as in what do I get after removing hydrogen, right, as H plus. So this will be what I have. Okay, let me draw it in a slightly different way. So generally, what we say is that if whatever group you have attached, that can kind of pull away your electrons from this oxygen, right? So some way or the other, take away negative charge and delocalize it from being localized here. That stabilizes the conjugate base, right? So as far as this benzene is concerned, benzene by itself is something that can pull away this negative charge. So yeah, benzoic acid is acidic, right? But when I'm looking at this OH group or my OCS3 methoxy group, these are both minus I as well as plus R. And this plus R is more damaging than effect of minus I. Minus I inductive effect, right? Electron withdrawing effect because of what you call as electronegativity, higher electronegativity of oxygen, that is there, but that is only till like 2, 3 carbons till where that effect is kind of felt. So this OCS3 or OH, even though they have minus I effect, they can't stabilize the conjugate base. If this is stable, implies more acidic hydrogen, like how we have seen earlier questions involving carbon hydrogen bond energy and stuff. Similar story. So if your conjugate base, we say that after removing whatever we get as anion is called the conjugate base. Right? And this conjugate base, specifically what I've drawn here is your benzoic acid, benzene carboxylic acid, if you want to call it like this. So this benzene ring has a minus R effect. It will take away that electron cloud because of resonance. So yeah, of course, what we are going to see is that benzoic acid is decently acidic, but the presence of any electron donating group here, like OMe, is going to destabilize the negative charge. This is something that will pump in electrons into the system, right? So charges anywhere in nature is not good. So if somebody would kind of delocalize or take away or scatter that negative charge on the oxygen here, then it would have been really stable. But OMe and OH, both of these are electron donating groups, are not good for us. But as far as this one is concerned, you can see this is good for us because at para position we have chlorine. Of course, chlorine has a minus I effect. It's the third most electronegative element after fluorine and oxygen. So it does have an effect. It will kind of reduce the negative charge on the conjugate base, take away that negative charge surplus from your O minus. So this is going to kind of make it stable, right? So this is stable. I mean, the conjugate base is stable, which means that this is a decently acidic hydrogen. This is better than benzoic acid. Chloro group is only going to make it stronger than benzoic acid. Benzoic by itself was also like because of minus R effect of benzene ring. It's a stabilizing thingy, but presence of chlorine is only going to make it better. Now here, the interesting part is we have OH here, right? So this is called the ortho position, right? And anything at ortho, of course, I do understand it is OH, so it is a one with lone pair, so it should be something that has a plus R effect. Here we did speak about the plus R effect in the A molecule, right? But we are not going to speak about that here because, of course, it has that effect everywhere. But here, this is called ortho effect, right? So I'm sure you might have heard of this ortho effect. Irrespective of the nature, right? Irrespective of what kind of substance we have here, because of steric crowding, what we see is that it becomes more acidic. This carboxylic acid that we have ends up being more acidic. This is called typically ortho effect, irrespective of what we have. Right? By what we have, what I mean is that irrespective of whether it is electron donating or electron withdrawing group, Cl, Br, Me, OH. Me is something with mine plus I effect. If I had a methyl group, methyl is something that gives electron, like OH is using resonance, or it is using what you call as R effect. Methyl group does have plus I inductive effect, but even a methyl group at this ortho position would have made it more acidic because of crowding or because of what you call as ortho effect. But again, here there is one more angle to this. There is that stabilization of conjugate base that is going to happen because of intra hydrogen bonding as well. So you have an OH like this, there is going to be a intra hydrogen bonding that is going to stabilize your anion a lot. So even here, what you're going to see is that this is more acidic than your benzoic acid, and your parachlorobenzoic acid is also more acidic with your OMe and OH groups with plus R at para position. It is not good for the conjugate base stability. So yeah, these two will not be something that is stronger than benzoic acid. They're going to be weaker than benzoic acid, right? So yeah, of course, many of the concepts from JE 11, 12th and all are also involved here. I hope you had a decent paper. All the best. See you.